Okay, we're going to get started again. So we're down to our final two talks for today. So our next talk will be, I probably should unblink the monitor there. Our next talk, Dr. Vito is going to talk about solar thermal systems. And then I'm going to talk about combined heat and power systems. And then we'll just have some closing discussion and finish things off. So Dr. Vito, let's get you set up here.
Okay, so this will be about solar thermal system and how can we use it to be a source of heat instead of natural gas in the process heating for industrial facilities. So as you know, any facility will go, we consume electricity and heat. Okay, so the previous presentation was solar PV, provide them electricity using solar PV. This one will be about providing them heat using solar PV. Okay, so these are the main points that I will talk about: the U.S. Department of Energy, industrial decarbonization roadmap, and I will define the solar thermal and the main system components, and then the system design and the performance. And finally, I will introduce a very simple tool for the Department of Energy, developed by the Department of Energy, that will give you a very quick estimate how much is the savings that you can do after implementing solar thermal system. Okay, so in terms of the carbon dioxide emissions, if you look at the different sectors nationwide, commercial, industrial, transportation, and so commercial, residential, industrial, and commercial, residential, transportation, and industrial. The industrial weighs about 30% of the carbon dioxide emission. Okay, and some of them come from the cement industry, food industry, iron and steel, chemicals, and refining. Okay. And the energy consumption by sector as well, I will say commercial, residential, transportation, and industrial. Okay, so the industrial accounts for 33% of the total energy consumption nationwide. And this comes to 31,000 tera BTU. And again, these are the breakdown of the percentages: cement, food, iron, and steel, chemicals, refining. And all of these industries needs heat. Food needs heat, cement needs heat, iron and steel for sure, chemicals, refining. All of these industries are heavy in the heat demand. And looking closer to the breakdown of energy use for the manufacturing facilities, you'll see that about 50% of the energy is consumed for process heating. 50% of the energy consumed is for process heating, and the other 50% is distributed according to all of these units. So let's focus on the process heating. If we are able to deliver the heat they need for the process using clean technology, I mean by clean technology without carbon emissions, then we will solve at least 50% of the carbon. Okay? And dividing also the heat requirements according to the temperature. So you need heat, but at what temperature you need this heat? Okay, it depends on the process or the manufacturing facility you have. So for chemicals, refining, food, iron, cement needs very high temperatures, over 1100 degrees C. But food, all what you need for food is maximum 150 degrees C. Okay? 150 degrees C, it can be the boiling point of water at a higher pressure, right? Can increase the pressure to make the water boil at 150 C. And this will not be a very high pressure. Okay. And chemicals, a lot of the chemicals needs just maximum 150 C. So a good candidate for these low temperatures is solar thermal. Okay, and if you look at the cumulative energy for all of these processes, you will see most of it less than 200 degrees, right? The horizontal axis is the temperature, and the vertical axis is the cumulative energy. And most of the energy is consumed at temperature less than maybe 220 or so, right? 220 degrees, right? So if you can deliver the heat at temperatures less than 220 C using the clean technology or zero carbon emission, this will solve the majority of the problem of carbon emissions from the industrial cities. Okay, and here it comes the two options. You can deliver the heat by mainly two options. Or I mean, two options for zero carbon emissions. Okay? You can deliver heat by other options with carbon emission, what they use right now, propane or natural gas combustion to deliver heat. But if we look at the options with zero carbon emission, so you can use solar PV and heat pump. The heat pump needs electricity, and you can give this electricity from solar PV, zero carbon emission, and that's it. Or the other option is solar thermal. You can convert the solar energy into thermal energy directly, and that's it. So the first option, solar PV plus heat pump, so you have the efficiency of the solar module is about 20% efficiency. Okay. And then you have a backup battery for this system. So you can use the energy during the night as well. And you have the inverter, as we said, to convert the DC to AC. And you have a backup from the grid. And then you have the heat pump. Okay, so the inverter here, efficiency is about 95% efficiency. And then you have a heat pump of 2 or 3 COP coefficient of performance. Some advanced heat pumps can go up to 4, maybe 4.5, but they are very expensive. Okay, and they may affect your payback period of the project. And finally, after the heat pump, you have hot water or hot air. It depends on what you need. Okay, and that's it. You delivered the heat supply or heat on the. The other option is to have a solar thermal system, and now you have the sun is delivering the energy to the solar thermal system with efficiency 50%, and this efficiency goes sometimes up to 60%. And I will show you a real experiment for us, a real solar thermal that I worked on during my PhD. The efficiency goes up to 60% for some time of the year. And then from solar thermal, you can use directly the hot water or the heat transfer fluid, whatever it is, water, oil, whatever it is. You can use it directly to your manufacturing facility as a source of heat, or you can use heat exchanger with efficiency maybe in the range of 95%. And finally, you have the hot water. Okay. And I'm talking here about hot water because most of the food industry, they just need hot water. Okay. So you remember the previous figure, if you are able to cover the food industry, okay, with zero carbon emission heat supply, this would be a good achievement by itself. Okay, so these two scenarios has like a competition between these two. If you calculated the overall efficiency of the first scenario and the overall efficiency of the second scenario, they are almost close. Okay, calculating the total efficiency is 20 times 95 times 2 or 3 times 90%. This will give you the overall efficiency of the process. And for the solar thermal, you multiply 50 times 95 times 90%. That will give you the overall efficiency of the process. And you will find that these two numbers are very close. So you have the two options to use this option of the solar thermal. Okay, but here we will focus on the solar thermal preheat process. Okay, so again, solar thermal is used to convert the solar energy to heat. Okay, and this can be by two main designs or two main systems: the tower, and usually they use it for massive amount of generation. This one is one of the power plants in California, 4 miles and 3 miles. It's very huge. These dots you see here, these are the locations of the tower, and all of these surroundings are heliostats or mirrors to collect the sunlight and reflect the sunlight to the tower. And the temperature at this point of the tower reaches up to 1,000 degrees C. Okay, so they have maybe molten salt or some material heated, and then they use gas turbines to convert this heat to electricity. The other way is to use the what we call it collectors, solar thermal collectors or reflectors, and it is mainly the main design here is the parabola. Remember from math and mathematics course, you have the parabola and you have the focus point. Okay? If you have light going to the parabola, it will be focused in the focus point of the parabola. This is the main concept here. So you have a parabola, and all of the sun light comes to the parabola and reflected to the focus point. And at this focus point, you will place your heat transfer fluid or the tube that has the heat transfer, so it can receive all of the collected sunlight. And once it is hot, you can circulate this fluid in the system and make the process continuous to deliver the heat you need. Okay, so this is a real system that I worked on during my PhD. It is mainly 2 modules. This is one module, second module, and each module is 3 collectors. And each collector, for sure, it has a tube inside which you have the fluid, and you have a tank, a hot water tank, have a pump, have flow meter, some connections here between the system and the tank to store the water and to receive water as well. And you have some thermocouples to measure the temperatures at different points of data acquisition system to collect some data, and the biometer here to measure the solar irradiance. And we collected the data for every minute for full year 2022. I will show you some of these data after a few slides. And this is from the front. You have the east-west tilt to allow the rain to drain from the sides of the system. And if you are building more bigger systems, these systems are built by Winston Kuhn Optics. This is a company that funds part of my PhD, and I work with them on these systems. This is a 50-meter squared system. It was built to deliver 24/7, 80 degrees C hot water, and 20 foot. For sure, we don't have sun during the night, but we have thermal storage. We are storing the hot water in a huge tank, and we then use this water during the night. Another system, this system uses oil to reach to higher temperatures. The temperature range generally for solar thermal, it can goes up to 300 degrees C, but it depends on the application and the heat transfer fluid you have and how much is the flow rate inside the system. The higher flow rate, the lower temperature. Okay? The less flow rate, the higher temperature you can achieve. Did I say it wrong? The higher flow rate, the less temperature goes opposite. The less flow rate, the higher temperature you can reach. And this system was installed in a dairy farm. We need hot water for the milk process, pasteurization, I think. They were using propane, and they replaced the propane system by solar thermal system. Okay, so going inside the system, again, this is a module, and it has three reflectors or collectors, and mainly the design is parabola. They are playing with the design a little more. It depends on the tilt of the module. If you want to place the module horizontal on the ground, or if you want to place it tilted. Okay, so you change the design of the parabola to collect as much sunlight as possible to increase the temperature and the collected energy. And there is softwares you can play with to design these collectors. But anyway, so you have this tube in this collector. So this is a collector with a mirror surface. Collect the sunlight over this tube, and this tube, it has this receiver. It is usually this couple, and then this two little tubes has flow in and flow out. So inside the glass tube, this is glass tube. Inside the glass tube, it has you have two little tubes, one on the top, one on the bottom. One is in, one is out. Okay, so the flow will go in and make a U-turn and then go out of the glass tube. And usually this glass tube is in vacuum, so it has vacuum inside to minimize the radiation heat losses to the surroundings. And looking at the system from inside, again, this is a flow of the water. So it goes from the tank, water pump, flow meter, and then goes inside the first tube, second, third, fourth, fifth, sixth, and then going back to the water tank. Again, in this case, we are sending the water to the tank again. We don't have a real load connected to the system, but if you have a real load connected to the system, so you will place your load here so it can consume the energy from the fluid. Okay. Any questions so far? Any questions from online? Okay. Okay, so looking at the system performance, how can we measure the efficiency of this system? You can do it by two ways. You can divide the thermal energy you will get from the fluid over the solar energy, how much solar energy you are receiving, and how much is the thermal energy you are delivering. Divide these over each other, and simply you will get the efficiency of the system. Or you can calculate it using the eta node, what we call it the optical efficiency of the conductors, minus the thermal losses over the solar power or the solar energy. And the eta node, the optical efficiency here means it measures actually the efficiency of the reflectors or the conductors. It measures the efficiency, how good are they in collecting the sunlight in one point or in one line. Okay? So the higher this efficiency means, the better you are collecting the sunlight into and concentrating it into one line. Okay, and usually this efficiency is between 70 to 80%. And then you have some losses. This loss is mainly due to radiation. We are trying to minimize the radiation as much as possible by using vacuum inside the tube, but still you have some losses, especially if you have very high temperatures up to 250 degrees C or so, you still have heat losses. And the Q solar, this is the amount of solar you are receiving from the sun based on the location you have, and you can measure the solar irradiance or the solar insolation, and based on this, you can find how much is the Q solar. The thermal energy, this is the thermal energy delivered to the load. You have the mass flow rate of the fluid, the CP, the constant, the specific heat at constant pressure, and the delta T, the temperature difference between in and out. The fluid goes inside the system with, let's say, a room temperature, and then leaves the system at, let's say, 250 degrees. There's a temperature difference between in and out of the fluid times the specific heat at constant pressure, CP, times the mass flow rate of the fluid. This will give you the thermal energy delivered to delivered from the system. And then the solar energy, you have the solar irradiance times the collector area. You have the collector area times the solar irradiance is measured value, or It can be from the database line, the NSRB. You can download how much is the solar irradiance every 5 minutes in any location you want from the NSRB database. Okay, so using these equations, you can calculate the efficiency, and this is the efficiency of the system I showed you at the beginning. So the vertical axis on the left shows the daily solar and thermal energies, and the right vertical axis shows the efficiency. Okay, so and for sure these are the months of the year 2020, and these are real data. So we collected these data, 1 minute data, and after some processing for the data, we got this figure. So the solar, the yellow dots, okay, it is increasing with the month of the year, reaching to the maximum around June and July, and then decreasing again. And then you have the thermal energy. It follows the same trend of the solar, and it does make sense. The more solar you have, the more thermal energy you can deliver. Okay? And the efficiency, it goes up to about 60%, very close to 60% at some time of the year, and then decreases other times. And we found that during these 2 months, June and July, the efficiency started very high at the very beginning, and then decreasing, and then you have jump, and then decreasing. Okay, and you can see also the same trend here in May. You have decreasing efficiency, and then jump, and then decreasing, jump, and so on. So we tried to figure out why it jumps suddenly every month or so. And the main reason was clean collectors and dirty collectors. So this is the efficiency for, I think that was for June, okay, or July, one of the 2 months. So the efficiency starts with 60 plus, maybe 65 or so, and then decreased to 55. So we found that every day the efficiency is decreasing by about 0.5% due to soil. So this is the shape of the collectors, very clean collectors, and then this is by the end of the month, a lot of soiling, a lot of dust. So one of the main important points of having this solar thermal system, you need regularly to clean the system to keep the efficiency as high as possible. I think here in Houston area, it is raining at least 1 time per week. So it will be automatically cleaned. You don't need to clean the system. Or what you need to just adjust the tilt so the rain will, so the drain of the water will go from the sides of the system. Okay, so any questions so far? No questions online? Okay. Okay, so here I will introduce the tool. It is a very simple tool. It is a spreadsheet. You can download the spreadsheet from this link on the Department of Energy website. And all what you need to do is first input a desired solar fraction to be evaluated. This number, you will ask the facility manager or the facility personnel how much is the energy, how much energy used, and then you can run some simulations, different simulation based on this number, changing this number 30%, 50%, 100%. If you want to deliver all of the heat requirement from solar thermal, it will be 100%. 50% of the heat requirement from solar thermal will be 50%, and so on. And then estimate the building's daily hot water use. It can be hot water or it can be another fluid, it depends. And this data you can get from the client. You can ask them how much daily use of the water or of heat, and you can convert this heat to water flow at specific temperature. And then the cold incoming water, this is usually the ambient temperature in the location of the facility. Again, you can download the ambient temperature from the database, the NSRDB, and download the ambient temperature in any location you want. And then the hot water delivery temperature. This is also required from the client. How much is the temperature they need? Okay. And then the cost of the electricity, and you can find this from the bills, how much they pay for kilowatt hour, or how much they pay for fuel, if they are using natural gas, or if they are using electricity for heat. Okay, and then you will also include the maximum daily solar insolation on tilt equal latitude. You remember the maximum solar irradiance you can receive based on the tilt angle, and the best tilt angle you can use is the latitude tilt angle. And this is given in different sheets. So the spreadsheet has different sheets, and one of the sheets showing you how much is the latitude and longitude for each city nationwide. So you select one which is very close to the facility location and use this as the tilt angle. Okay, and this should be a good rough estimation for the tilt angle for the facility location. And then the average daily solar insolation on tilt equal latitude. Again, another sheet in the spreadsheet shows you for each city nationwide how much is the average daily solar insolation. Or what you will do is select the number from this spreadsheet based on the city that is close as much as possible to your facility. Another way is to do it by going to the NSRBB database and download the data from this location and calculate how much is the average daily solar insolation. But again, they gave you some good estimates for different locations nationwide to help you to do the calculation very fast. It was in a couple of minutes you will get it done. Okay, so next, some economic results. You have here the simple payback period and the saving to investment ratio, and this ratio should be more than 1 for sure. If it is less than 1, it means the system not worth it. It's better to use another technology to deliver the heat. And yeah, that's it. This is a very simple tool, very fast to use, and they gave you all of the data that support you to finish it very fast. All what you need is to ask the client for these two questions. How much is the daily hot water consumption? How much is the hot water temperature? And how much is they pay for electricity or natural gas? And yeah, any questions? It should be very simple. Again, if you wanna do it more accurate, you can use SAM software to get more accurate results. Another softwares similar to Helioscope, they do the same, but for solar thermal. They do the design over the roof, and you will follow very detailed steps to get it very accurate. But at least this tool will give you a very quick estimation on site. Ask them these two questions. Previously, you have the bills, you know how much they pay for electricity or gas, and you can do this calculation very fast while being in the facility. Yeah. Thank you.
You have one question
Yes.
Online.
Mm-hmm.
For the pulp and paper sector, most of the natural gas usage is dedicated to the drying process. The DOE roadmap mentions that we can potentially electrify this process. Do you have any idea or case study for the electrification of drying process in the pulp and paper sector for any process temperature around 230 Fahrenheit, maybe integrated with PVT?
Good question. A long question.
Yeah. So,
okay, so he's looking at what other maybe method to deliver heat at 230 degrees Fahrenheit.
Specifically for drying processes in the pulp and paper sector.
Okay, and electrifying the process instead of using natural gas. Is true?
Drying, yeah.
Yeah. So I think you can use PV to generate electricity, and you can use this electricity with zero carbon emission to heat up to deliver the heat to the process. But I'm thinking about solar thermal is not a good candidate in such a process because you need to remove water, right? It is drying it's a process of drying the paper, you said, right? Paper? Yeah. So I think solar thermal is not a good candidate for this. Do you have any?
Yeah, I can.
Sure. Right.
I actually can answer that question. Texas A&M, University of Pennsylvania, and Virginia are all, there's an ARPA-E project targeting that specific thing. Decarbonization of drying and pulp and paper industry, and particularly lumber drying as well. And the technology that they're pursuing for that is an augmented heat pump system with a specific Kirigami-based desiccant system. So if the person who had that question wants to send me an email, Rassmussen@TAMU, I'll get them connected with Dr. O'Neill and her team who are doing that exactly thing. So they have a pilot, they're in the 3rd year of that project. And so they have a pilot demonstration actually out on our satellite campus where they're currently doing tests. So that's not a commercially available technology yet, but that is the exact problem they're trying to solve. So, all right. That brings us to combined heat and power. Okay. Okay, and I understand that I'm the last thing standing between you and your weekend, so I will try to go fast, but this, as fair warning, the last time I taught this material, it was a full semester class. So I've tried to take all of my lecture notes and everything we taught and condense it into 30 minutes. So forgive me if I oversimplify at times or something, but this is a great topic. Okay. All right. Okay. So combined heat and power in its simplest terms, it is where we're going to, instead of buying electricity from the grid and then buying natural gas for our heating processes, we are going to buy natural gas and we're going to combust it, drive a generator to generate electricity, but then use the waste heat from that process to meet our heating needs. So instead of buying 2 things from the grid, we're going to buy 1 thing and become, in essence, our own local power plant. Okay. And the idea is that you can save money because you are leveraging the waste heat that comes off of that combustion process. So this is a very simplified diagram of that whole idea. This is sometimes called cogeneration because you're generating both electricity and heat, but combined heat and power is probably a better term because the variations on this diagrams can get very complex. You can have tri-generation situations. You can have staging of different turbine technologies and things like that. So, but the idea is very simple. Now, what gets complicated is sometimes the technologies that are used. So in particular, when we go back to this idea, we have what we call when we go to our engine or prime mover here. So we use the term prime mover to denote this first piece of machinery that is we're going to generate electricity with. Okay. Our prime mover technology can take a couple of different forms. Okay. Now, on the left, I want you to look at this graph for just a minute and see what you can deduce. On the left, you have the number of CHP installations. So this is quantity, how many times you have an installation of a particular type of CHP. And on the right is the capacity, meaning of all the electricity generated by combined heat and power technologies, which ones are generating the most electricity. So what you see is there's some key technologies here. reciprocating engines, steam turbines, gas turbines. Those are your three prime technologies. And then you also have fuel cells and microturbines as a kind of a secondary thing. So first, what is the first conclusion that you draw from these graphs about what's the difference in prime mover technology? Let me give you a starter. What can you tell me about reciprocating engines? Anna?
They're easier to install, they're more commonly installed.
They form the majority of installations. So if I just count up the number of combined heat and power installations, reciprocating engines are 55% of them. But what do you see from the graph on the right? Their capacity is small, which means you're going to use reciprocating engines. Most of the installations will have them, but they're not generating huge amounts of electricity. They're generating modest amounts. So for a small to medium manufacturing plant, what technology are you most likely to use? Reciprocating engine, right? Just from the statistics, that's what this tells you. On the other side, gas turbines, only 50% of the installations include a gas turbine, but they make up 64% of the energy generated, which means these guys are, where are you going to find the gas turbines? The big power plants, right? On Texas A&M, we have a combined heat and power plant. It has a gas turbine, okay, among other things. Okay, so let's go through and just talk a little bit about each technology briefly. So gas turbines in and of themselves have kind of two different forms. One is an aeroderivative gas turbine. That's another way of saying we take a jet engine and we convert it to be used on the ground to generate electricity, okay? But basically the same type. Or a stationary mainframe gas turbine. So something that was designed essentially to be a stationary thing. So essentially what you do is you bring in air, you have a compressor, you bring in air, you send that compressed air into a combustor with your natural gas fuel, and you combust it, which drives a turbine. Some of that turbine work drives the shaft, which drives the original compressor, and the rest of the work goes to an electric generator that gives you electrical power. And then what comes out of the turbine is your exhaust gases, which contain a lot of heat energy. And that's where we're going to recover heat from. So we generate both electricity and we generate heat that we can use for our processes, okay? So in an effort to use public domain or images where I could find credible sources, here's an example of a gas turbine installation at a university power plant like ours. So that gives you an idea of kind of size. This is the combustor where they're pulling in air down in here, and then you go through you go through the compressor, you go through the combustion, and then right in here is where you're gonna get your exhaust gases coming out, and then the shaft that drives the generator. Steam turbines are a little different. So for gas turbines, we bring in natural gas and we combust the gas to generate electricity. Well, what if you already had access to steam? Okay, look, for the sake of argument, you've already got steam. Well, then if you've got high pressure steam, you bring it in, you send it through a high pressure turbine, you extract some of its energy, and now you've got medium pressure steam that you send through a second turbine, and then after you extract more energy, then you've got low pressure steam that you send into a low pressure turbine, and then you get some exhaust out of here, and if you're smart, you put them all on the same shaft here so that they're all contributing work to the generator, okay? Now, hang on to this image for just a second. You may think, well, why is Dr. Rassmussen talking about steam turbines? You'll see in a moment where they come into play. The last one we're going to talk about is IC engines or reciprocating engine technology. This is, again, like the technology you're familiar with, diesel engines, gas-powered engines. Essentially, you're driving an engine that drives a shaft that runs an inverter and generates electricity. And what kind of fuel are we talking now? We're talking about diesel, right? You might use diesel instead of natural gas to run your IC engine, okay? Or you can run natural gas under a spark ignited cycle and so forth. But this engine's gonna get hot, just like the engine in your car creates heat that you have to dump out of the radiator. It's gonna generate heat, but we're gonna send that heat through a heat exchanger, and we're gonna then use a hot water tank and things, and we're gonna generate hot water that we can use in our manufacturing process, okay? So a couple of different types of technologies you can pick. Here's a picture of a reciprocating engine. Kind of looks like the V6 engine in a truck, except it's like a what, a V12 or a V20, right? But same basic idea here, right? It's the same fundamental technology. Okay, let's look at how some of these might come together. This is the diagram for the CHP plant here at Texas A&M University. For those of you on campus, this is right next side of the north side garage here, parking garage. So what do? They bring in natural gas and they use a gas turbine engine that with a generator that generates electricity. And that electricity either goes to power the campus, or it can be fed back into the grid, or it could be, we use it to drive electric chillers, because at Texas A&M campus, we use a lot of air conditioning in the summer. And so we'll use electricity specifically for chillers to keep our campus cool. Now, we use natural gas in this gas turbine engine, but then we've got exhaust gases, which we then send through a heat recovery steam generator, or HRSG, commonly known as a HRSG, okay? And we generate steam. And this is steam that's at a pretty high pressure. 600 PSI is higher than what you would see at most manufacturing facilities. And that high pressure steam now goes to a steam turbine. Remember, I said we'd come back to it? So now that steam turbine is hooked to a generator that generates even more electricity. Plus, after we're done with the high pressure steam, we're gonna pull out two different pressures of low pressure steam. So two slightly different temperatures. And they're gonna be used for hot water heating and then steam heating of campus facilities, as well as we're using steam. And in Texas A&M, they have about 10 big chillers, and these are huge chillers. And 8 of them, I believe, are electric, 2 of them are steam driven. So they're absorption cycle steam driven chillers, so that we're actually using steam heat to generate cold water that goes to campus. And then some of this cold water actually goes to a chilled water storage tank that we use as a thermal storage tank on campus as well. But you can see how combined heat and powers, they can get quite complex, right? When you're looking at a power plant style configuration. But they're also very highly efficient in how they utilize all the waste heat, okay? If you dig through the DOE literature, you're gonna find there's documentation. These are just screenshots of some of the DOE fact sheets that do a really nice job of comparing the different technologies, both in terms of what are the typical sizes you're gonna see, what are the efficiencies you can expect, what are the installed costs, what are the operation and maintenance ongoing costs that you should consider, power to heat ratio, we'll come back to that in a minute, okay? So comparing different technologies from IC engines, gas turbines, microturbines, fuel cells, steam turbines. They'll also talk about things like part load efficiency. This is something you need to pay attention to if you've got an application where you aren't going to be running it at full speed all the time. Now, to be honest, the best scenarios, the places where combined heat and power will be the biggest money saving opportunities for your clients, is if the client runs 24/7, they're running all the time, and their electricity needs are very constant and their heating needs are very constant. But if their heating and electricity needs fluctuate, then that probably means you might be operating your combined heat and power at only part of its design load. And some of the technologies are better at part load than others. So like gas turbines, they're meant to run at full load, and that's where they do their best job. IC engines, they do a pretty good job at both full load and at part load conditions, okay? It's still better to run them at full load, but they do at least work fairly well, okay? All right. I told you I'm going fast here. So just a summary of some advantages and disadvantages. Steam turbines, very reliable, usually best for large systems. Depending on how you use them, their efficiencies might be a little low. Gas turbines, you get really high exhaust gas temperatures. So if you've got a manufacturing process that needs really high temperature heat, this is the technology you may need to go with. But you're also looking at typically very large systems. 500 kilowatts is a lot. And then IC engines, you get very high efficiencies. It's a fairly straightforward technology. It doesn't necessarily require, you are going to need to hire people to run this, but an IC engine plant is a lot easier to run than, say, a gas turbine plant. But they're going to have some maintenance needs that you need to pay attention to, okay? All right. Let's talk about design, okay? I look at my facility and I say, okay, here's a facility, they use a lot of electricity, they use a lot of heat. How do I pick the size of my combined heat and power system, okay? Ideally we buy a combined heat and power that provides exactly what electricity we need, and its waste heat is exactly how much heat we need. What are the odds of finding a combined heat and power plant that does that? Basically never, right? It just doesn't happen. It just doesn't happen, okay? Which means you're going to be designing to meet one of your loads, but not the other, okay? So for example, if you want, you can design your combined heat and power to meet your electrical load, and then depending on which technology you pick and depending on what your heat needs are, you might not have enough thermal power. So in that case, what are you going to do? You're going to do what for thermal power?
You're gonna have to like generate it some other way.
You're going to generate it some other way. Now, conveniently for us, as ITACs, we're typically coming in and recommending combined heat and power to replace equipment, which means if we're not going to provide enough steam heat for them, they probably already have a boiler that they could use to provide the supplemental heating that they need. Or if we're not going to provide quite enough hot water to cover all their hot water needs, well, they probably already have some hot water heaters, right? So if we could match their electrical power, we may not provide enough thermal power, but then we use auxiliary boilers or hot water heaters to provide what else we need. Or what happens if we match their electrical load, but our technology produces more waste heat than we need? What's going to happen? It's going to go to waste, right? So typically not the best option, right? All right. Well, what if we match the thermal power, but we generate too much electrical power? Well, that's generally fairly straightforward to handle. We'll just sell it back to the grid. Or if we match the thermal power and we don't have enough electrical power, we're just going to buy some for the grid. Now, the truth is, for most of the clients you might be working with, even when you're recommending combined heat and power, the combined heat and power system that you recommend is probably not going to cover their electrical needs or their thermal needs. You're probably going to be under-speccing both things, right? But if you were in a position where you were trying to actually fully cover one of the loads, it's probably better to design to meet the thermal loads and then handle the electrical loads either by buying or selling to the grid, okay? Or match their electrical load and then use auxiliary boilers as you need. Okay, so this is the same information, but just drawn kind of on a graph and pictorially, so you can get a feel for this. So essentially, at some point you would want to graph, where am I on my electrical power? Where am I on my thermal needs? I can kind of mark where I want on my thermal needs. Ideally, I would be here at spot 1, but that's probably not going to happen. So I either need to pick a technology that's on this line, the green line or on the black line. Now notice that one of these lines produces more thermal than it does electrical, or rather, and then the other produces more electrical than it does thermal. We call that the heat to power ratio. Okay. So this is data. I know this looks old. It is a little old because it's drawn from an older textbook, but what I really like about this is they're not telling you what units they're working in because they got hold of proprietary data. So each of these squares is were commercial systems. And what they're showing you is for gas turbines, what do we typically see on our heat to power ratio here? Now again, arbitrary units here, but if you look at these, you can basically draw a line through that and you see that for gas turbines, we're generating more heat than power here, right? Or rather, we're generating a lot of heat for the power that we get. If you compare that to IC engines, the reverse is true. IC engines produce mostly power and then a little excess heat on top of that, okay? So let's put these two pieces of information together. Let's put this information together with what we talked about at the very beginning with the number of installations. The technology you're most likely to recommend to your clients is what? IC engines. They're a little bit smaller. They're generally going to be what generally sized for what you're doing. But what that means is you're going to be producing not as much waste heat, right? So in general, that's probably good for most manufacturers, right? Most manufacturers have higher electrical needs than they will have thermal needs, right? So again, IC engines is probably going to be your likely good option for manufacturing. Now, these are graphs that show kind of part load conditions. I'm going to skip through those in the interest of time, okay? I want to skip to this idea of a packaged cogeneration system or a packaged combined heat and power system. So as you can imagine, many of these systems are custom designed, right? To meet very specific needs and specific loads. That's not what you guys are going to be doing as ITAC students for the most part. You probably want something simple, you can look up easily, and then do calculations in a fairly straightforward manner to recommend the idea to the client. They may eventually, if they implement this, they may implement something that is more custom or something different. But what you're trying to do is provide enough of a convincing case for them to consider this technology. Okay? So the nice thing about these package systems is that single source responsibility. Instead of buying your heat recovery steam generator from one company and your electric generator from another company and your gas turbine from another company, if you buy a package system, it's from single source. So if something goes wrong, you know who to complain to, right? Right? Okay. They typically are designed to have faster installation times. You're not trying to integrate equipment. You're bringing in one thing on a package sled and just interfacing it with your plant, okay? And there's lower costs typically because you're spreading out the design costs over selling lots of units. The main disadvantage is not going to be a custom solution. You're going to look for something close, not something that's exactly what you want, okay? This is where the CHP catalog comes in. This is just fantastic resource for this types of things, not particularly because we're not interested in finding them the exact package that they're going to need. We're trying to find a representative solution that will get them to consider CHP for their problem. So what you do is you go to CHP eCatalog at oakridgenationallab.gov, and you can look at a list of package systems. You are going to plug in your zip code. You're going to plug in your target kilowatt size. You could select a prime mover if you want, or fuel, or thermal output type or something, but you don't have to. There's a couple of things you may want to pay attention to. On these systems, you'll see fuel type down here. And if you go further down, you're gonna see some other options like, is this system designed to be stackable? Meaning, if I want 50 kilowatts of capacity and this unit's only 10, is it designed that I can just buy 5 of them and string them together, right? Okay, you'll also want to pay attention to their grid connection in terms of some of the options. I'm not gonna go into the difference between a black start and a parallel connection and all those types of things. But those are things you probably wanna read the fine print and make sure it matches what your client's probably going to need, okay? But in any case, you do your sorting, it's gonna tell you, okay, there's a certain number of packages that meet your criteria. You can click on one of them and it's gonna tell you, what does it produce? Does it produce steam or does it produce hot water? You know, what's its grid connection type? And what's its power output in terms of electricity? What's its fuel, etc. It's gonna give you information like, how many times has this package been installed? How many has been installed in Texas? Well, this one, none, right? How many has it been installed in this particular configuration? So you get an idea if this is a new thing or if this is something that's well established. All of the data is going to be organized this way that makes it really nice. You can say, okay, at 100% gross power, meaning if I run it at full load and the outside temperature is either 0 degrees Fahrenheit, which is really cold, 59, which is cool, or 95, which is Texas, okay? What is our fuel input? In other words, how many MMBTUs of natural gas is this going to consume? What's the electricity output that it'll produce? And then what is its hot water flow? And what are the temperature differences between supply and return temperature? Or in other words, what is the hot water heating capacity? Okay. And so this allows you to calculate exactly how much electricity that this will provide that you won't have to buy from the grid. Exactly how much heating capacity will this provide that you won't have to use your boiler for or your hot water heater for, and so forth. And it makes the economics calculations pretty straightforward, right? What are my inputs? I'm gonna have natural gas. What am I gonna get out? I'm either gonna get out steam or hot water, and I'm gonna get out electricity. Why am I saving money? Because, well, in this case, my natural gas bills are probably gonna go up. Well, they are gonna go up if you use a natural gas fired system. Before, you were purchasing natural gas just for your boiler or your hot water heater. Now, you're purchasing natural gas for your combined heat and power system, plus whatever natural gas you need for any leftover boiling, some supplemental boiling you need. This means that your natural gas bill is going to go up, but your electricity is going to go down, right? Before, you were purchasing all your electricity from the grid. Now you can subtract off the electricity produced by the CHP, both in demand and in kilowatt demand and kilowatt hours consumption. And so you can calculate savings. If you were to guess which of your utilities is more interested in you considering combined heat and power, your natural gas supplier or your electricity supplier? Your natural gas supplier. So if you're seriously considering CHP, it becomes a great time to revisit your contracts, both with your natural gas supplier to say, look, we're considering this. If we go with this, we're going to be buying a lot more natural gas. What kind of, can we renegotiate our natural gas price? It's also a good time to talk to your electric utility company saying, hey, we're thinking of going with a combined heat and power plant. Is there anything, can we talk about our electricity price? If you can give us a better deal, we may not be worth going to considering combined heat and power. So whatever your path forward is, it's probably a good time to talk with both of your utilities to talk about your rate plans, okay? Because these are not small changes in how much energy you're using. This is a pretty sizable shift, right? Somebody's going to be making money, okay? I think, and with that, that's all I wanted to try and cover today. gave you a little bit of information about prime mover technologies, a little bit about what to expect, the e-catalog to go to figure out how to purchase things, and a little bit about the economics. But also remember, if you find an opportunity to do a CHP AR, who should be your first phone call or who should be your first email? Not me, not your ITAC director. Remember the on-site energy TAPs? On-site energy technical assistant providers. They're the DOE programs that this is all they do. And they're interested in not just helping you with getting your calculations, but also they want to help the companies go through the process of adopting the technology. So they can be a great resource to help double check your calculations, make sure you're on the right path. Okay. All right. Any questions online on CHP? We've exhausted our audience of questions. Any questions from our in-person audience? Okay. All right. Well, then let's close things out with just a couple of items here. Okay. So if you grab your phone, look at get the QR code. For our online audience, we would also appreciate if you would take the QR code, fill out the post survey. That'll help us figure out what we can do better. And as we mentioned at the beginning, we plan to do these every fall and spring semester. So if you have requests for things to cover, suggestions for things that you'd like to see us do better, by all means, either put it in the survey or send me an email so that we can adopt that. But I hope this workshop is useful. I hope that it helps you be better equipped to maybe adopt some recommendations that you weren't comfortable doing before, but you might be comfortable now tackling and recommending to clients and get you access to tools. A couple things you should expect. If you registered for this, we got your email address. We will be sending you links to where you can download copies of all of today's slides, as well as our resource sheet that has all the hyperlinks to softwares and documents and so forth. If you have any other requests, please let us know. Otherwise, we'll let you go for the day. I will be jumping on a Zoom in about 10 minutes for anybody who would like to just chat one-on-one or ask any specific questions. It'll be this exact same Zoom link. So for those of you online, if you want to either stay on or jump back on here in about 10 minutes, I'm happy to answer any questions on a more one-on-one format. So, okay. And Shai, go ahead.
The first question is, what was the topic of the workshop? And it's just topic A, topic B, topic C.
I
Do you want
know,
us to
Hannah,
fix
I
them?
thought we fixed that, but it's okay. Ignore the first question on the topics, just pick your favorite letter. Okay. All right. I would like to, I'm obligated to mention again, these are not the opinions of DOE. And I would just like to thank all the people that participated today. Dr. Abito, Dr. Elliott, and then our students, Dig Vijay, Caleb, and Noah, thank you for your help. And Joanna for all the logistics and food. So thank you for your help. Have a great weekend, everyone.